Okay, so here's our upcoming schedule. 3-6 we're going to cover today is not officially on the test, and then we're going to review Wednesday, test the following Wednesday. Okay, so second order linear equations. Nothing new in today's lecture. We're just summarizing everything we know about the equation that models the harmonic oscillator, the second order differential equation, my double prime plus by prime plus ky equals 0. So m is the mass. So we're assuming that we derived this I don't know, weeks ago, where m was the mass, k is the spring constant, and b is a damping coefficient. Okay, and we derived this using Hooke's law and one of Newton's laws. So you can go back and review that if you can't remember the derivation. So this is said to be second order because we've got a second derivative in it. Linear because it's linear in y double prime, y prime, and y. And homogeneous because the right-hand side of the equation is 0. All right, so far we have developed two ways to solve this kind of equation. In chapter 2, we used something called the lucky guess. And in chapter 3, we converted to a system and solved it using eigenvalues and eigenvectors. So what we're going to do today is show that they're the same. They always give you the same thing. All right, so I'm going to do this two different ways. Solve this second order ODEs, just an example, using the two methods. So we'll start with lucky guess. So when we first introduced lucky guess, it seemed kind of, how am I going to just guess this, right? And we said, well, we're taking a linear combination of a second derivative, a first derivative, and the function itself and trying to get 0. So it seemed like an exponential might be the best way to try to find a function that would satisfy that. So our lucky guess was y equals e to the st. And now that we've done all of our work with systems, we know that the solutions to systems always are combinations of e to the lambda t, right? So this makes sense now in terms of all the work we've done with systems. Although it might make more sense to call that s a lambda, but a lot of engineering applications use s, mathematicians use lambda, so we kind of go back and forth so that you get used to both of them. All right, so if my lucky guess is e to the st, I'm going to plug into this equation and figure out what s has to be. That was when we were solving a first order linear non-homogeneous equation. That was a different thing. All right, so if y double prime, if y is e to the st, what is y double prime? S squared e to the st. And 7 times y prime, the derivative of my lucky guess y would be s e to the st plus 10 times y, which is e to the st, equals 0. All right, so then I can factor out e to the st, and I get s squared plus 7s plus 10. E to the st can never be 0. An exponential can never be 0. So it has to be the s squared plus 7s plus 10 is 0. And that factors to s plus 2, s plus 5. And we get s has to be -2 or -5. So now I have two solutions. I know I was looking for solutions that looked like e to the st, and now I have two different s's that will work. So I have my y is going to be, I have y1 e to the -2t and y2 e to the -5t. All right, and then one of the principles of linearity says that now I can take a linear combination of my two solutions. I just need any two solutions. They don't have to be the straight line solutions. Any two solutions that are linearly independent, right? That have an initial condition that don't point in the same direction. So I've got two solutions, two linearly independent solutions. Take a linear combination, and I'm going to get a function y of t, k1 e to the negative 2t plus k2 e to the negative 5t. Yeah, so, oh, yes, yeah. So what I've done here is my original equation was a second order. My unknown is y, a function y. And I found a function y that should satisfy this, the general function that satisfies this. This is called the scalar solution, okay, because it's just a single function y. The vector solution would be if I change this to a system, and then I would have a y and a v that were my solutions. So let's do that. Let's change this to a system. So I have y double prime plus 7y prime plus 10y equals 0. To change this to a system, I'm going to have y prime equals v, and v prime will be negative 10y minus 7v. So I already know the function y that solves this. It was k1 e to the negative 2t plus k2 e to the negative 5t. So v of t is just the derivative of y. V is just y prime. So now I take the derivative, and I'm going to get negative 2k1 e to the negative 2t minus 5k2 e to the negative 5t. General solution. So what I'm going to do to this general solution is I'm going to put it in the vector notation that we have been using for systems, just so that we can, when we solve it using eigenvalues and eigenvectors, we can compare it to this one. So I'm just going to change this to vector notation. So this says yv, right, is factor out, what am I going to factor out? Today I brought notes so that this wouldn't trip me up again. Okay, so I've got k2 e to the negative 2t times. Okay, so both of these functions have a, oops, k1. Both y and v have a k1 e to the negative 2t. The coefficient on the y is a 1, and on the v is a negative 2. And then both of my functions y and v have a k2 e to the negative 5t. So I'll put that outside. And then the coefficient on y is just a 1, and on the v is a negative 5. Yeah, so this looks an awful lot like e to the lambda tv, right? So these would be my eigenvectors, and my eigenvalues are negative 2 and negative 5. So we did all of this. We solved this without finding eigenvalues and associated eigenvectors. So this is a nice little shortcut. Sometimes, yeah. But the only systems that this works for is when y prime equals v. So like the first entry in your matrix has to be 0. Because it's 0y plus 1b. Yes. Okay, because that's fine, but then your vector is when you multiply, let's see, so you have y prime equals b prime equals -7. So you said 1, 0, -7, -10, your matrix, and you multiply that by yv. When you multiply this, you get 1y plus 0v and -7y plus. Okay, there you go. So if you multiply by vy, you can do it that way, but everything becomes vy. Yeah. All right, so now we've solved this whole thing without even using the word eigenvalue and eigenvector. So let's do it using eigenvalues and eigenvectors with all the methods that we learned in chapter 3 and just show that we get the same thing. I'm sure you believe that we will. So we have y prime equals v and v prime equals -10y minus 7v. So I could write this as a system. Y prime equals 0, 1, -10, -7 times y, using matrix notation. So the first thing I do is find eigenvalues, and I get them by taking the determinant of a minus lambda I. So eigenvalues, determinant of negative lambda, 1, -10, -7 minus lambda, set that equal to 0. So the determinant of this matrix, you do A times D minus B times C, so I have negative lambda times -7 minus lambda plus 10 equals 0. Multiply this out and you get lambda squared plus 7 lambda plus 10 equals 0. That equation should look familiar. We solved it. It's the exact equation we got back here when we were doing lucky guess, except we called it S before. S squared plus 7s plus 10. This isn't a coincidence. This is the characteristic polynomial, characteristic equation, and it pops up in both methods. Okay, so again, we get lambda equals -2 or -5. So we have eigenvalues. We have to find associated eigenvectors. Right, these are both real. They're both negative, which means this origin is going to be, I think, good. All right, so my associated eigenvectors, I solve AV equals lambda V, plugging in for each lambda. So A was 0, 1, -10, -7. Oops, plug lambda in there. So this says that V has to equal -2y, and my other equation, -10y minus 7v equals -2v, is equivalent to the first. So this is my straight line solution. That's the equation that I would graph in the phase plane to get my straight line solution. A vector on that line might be 1, -2. Right. Yes. Okay, then we do it again to get the eigenvector associated with the other eigenvalue. 0, 1, -10, -7 times yv equals -5 times yv. So I get v equals -5y. My second equation comes out to be equivalent to the first. So I have another straight line solution in the phase plane, v equals -5y, And a vector on this would be 1, -5. So I've got 2 eigenvalues, 2 associated eigenvectors. My solutions are the form e to the lambda tv, and I put them together in a linear combination. So let's see, I have y1, e to the lambda, which is -2, t v, which is 1, -2, and y2 is e to the lambda t v, v is 1, -5. So my eigenvalues and associated eigenvectors give me straight line solutions, and now I take a linear combination of these two to get the general solution. So y. Sorry, I should have little vectors on these guys. So y is e to the negative lambda t v, oops, k1 plus k2 e to the -5t 1, -5. General solution. And that is exactly what we got by doing lucky guess. Came out with eigenvalues and eigenvectors. So, and if I wanted the scalar solution, I could just pull it right out of here, right? If I just wanted y of t, then it would be k1 e to the -2t plus k2 e to the -5t. And v of t is the second component. -2 k1 e to the -2t minus 5 k2 e to the -5t. All right, so if I want to find the particular solution that satisfies the certain initial conditions, well, I know y of t, I just wrote these down, is k1 e to the -2t plus k2 e to the -5t, and v of t, which is y prime, is -2 k1 e to the -2t minus 5 k2 e to the -5t. I can just differentiate y. And then plug in your initial conditions. Y of 0 is going to give me k1 plus k2. And they told me that's supposed to be -2, +2. And y prime of 0, which is v of 0, is -2 k1 minus 5 k2 is -13. We solve this system by whatever method you like to solve systems with, substitution, and you get k1 equals 3, k2 equals -1. And then you would plug back in. You'd have to take these k's and put them in here, and that would be your answer. So that's a very common mistake on quizzes and tests and things, is for people to go like this and say, that's my answer. The answer is the function with the k1 and k2 plugged into it. Oh, yeah. Sorry. Oops. -1 and 3. Thank you. So do remember to go back and put them in. But I don't feel like writing it all over again. All right, so we've developed a nice shortcut for solving a linear second order ODE, it bypasses all the work of finding eigenvalues and eigenvectors. It works even if the characteristic polynomial has complex roots. So we'll do an example like that next. Nope. It doesn't have to be partially decoupled. It has to, any second order ODE, right? Like AY double prime plus BY prime plus CY equals 0. Any second order equation we can use this method on. So the question that a lot of people ask is, if we can do this, why do we bother with systems, right? So you can, whenever you're dealing with a second order ODE, you can bypass changing it to a system and using eigenvalues and eigenvectors. But not every system can be converted back to a second order ODE. So we do need the methods we developed in systems for some systems. All right, so we're going to use lucky guess to find the shortcut to find the general solution to this second order ODE. So we guess that y is going to equal e to the st. Plug in and we get s squared e to the st plus 4s e to the st plus 13 e to the st. Factor out e to the st, and we're going to have e to the st times s squared plus 4s plus 13. Yes?
If it doesn't equal 0, can you still do it?
No, we can't use this method. No. Well, there is going to be, remember when we started solving non-homogeneous linear equations, just a single equation, first order? First you solve the associated homogeneous, then you find a particular solution to the non-homogeneous, then you add them together. So it's the same procedure here if the right-hand side isn't 0. We're going to talk about it in chapter 4. Yeah. All right, so then we solve this. We get s equals, we're just going to have to use the quadratic formula because it doesn't factor. And we get s equals -2 plus or minus 3i. Just plug into the quadratic formula and simplify. So I'm going to have two solutions. y1 is going to be e to the -2 plus 3i t, e to the st, right? And my other one is e to the -2 minus 3i t. So if you remember when we talked about systems that had complex eigenvalues, we just looked at a single one of these solutions in more depth. So I'm going to just look at this one. Okay, I have a solution of the form e to the st, but the problem is that s is complex. So I'm going to use Euler's formula to put this into the form a plus bi, standard form of a complex number. So I have y1 is e to the -2 plus 3it. Okay, so distribute my t. And then I have like bases here, right? I could rewrite this as a multiplication problem. E to the -2t times, oh, sorry, this should, I already did the plus thing. Here we go. I just meant to distribute the t in that step. Then I can rewrite this as e to the -2t times e to the 3it. And then I use Euler's formula on e to the 3it. So if you remember, that says that e to the I times something is cosine something plus I sine something. So in this case, my something, my theta, is 3t. This is e to the 3t I. Okay, so I've got e to the negative 2t times cosine 3t plus I sine 3t. Distribute the e to the negative 2t. So now I've taken my complex valued solution, my e to the lambda t, where lambda was negative 2 plus 3i, right? And I've written it in standard form, a plus bi. Okay, this is the way we like to write complex numbers. Something real plus I times something else that's real. So remember from systems that we can break this into two solutions. I have two different solutions here. So since I was calling this thing y1, I'll call my two other solutions y2 and y3. The two solutions I can get from this. And the reason I like them is because they're both going to be real. I can take the real part, e to the negative 2t cosine 3t, and that's a solution. And I can take the imaginary part, e to the negative 2t sine 3t, and that's a solution. Right. No, well, no. So the theorem that I never proved to you, and you can read the proof in your book, but the theorem says that this piece is a solution and this piece is a solution. Just take the real and the imaginary parts. So I have two solutions. They're going to be linearly independent. So my general solution is a linear combination of those two. So my y general, a little g there for general, I get k1 e to the negative 2t cosine 3t plus k2 e to the negative 2t sine 3t. And that's my scalar solution because I only came up with a y. Okay? If I also wanted the v to solve this associated system, I would just differentiate this thing. It's a little quicker than finding eigenvalues and eigenvectors. It's nice. Mm-hmm.
So for make the jump to slide.
Yeah.
Is it okay to say that you're choosing a constant and you're calling it you're letting the constant negative I? That's why it's a solution.
Well, you're choosing, I guess we're choosing arbitrary constants. So the constant on this one's a 1. So these two are, so we could combine y2 and y3 in a linear combination and get y1, where the constant on this one's a 1 and this one's a negative I. Yeah. All right, so let's see what happens when we apply lucky guess to the general case, ay double prime plus by prime plus cy equals 0. So we guess y equals e to the st, and when I plug in, I get a times y double prime, which is s squared e to the st, plus b times y prime, which is s e to the st, plus c times y c e to the st equals 0. Factor out e to the st, And I get AS squared plus BS plus C equals 0. And AS squared plus BS plus C, that's our characteristic equation, the characteristic polynomial. So it turns out you can read it right from the ODE, right? A times S squared plus B times S plus C equals 0. So we can stop doing the little show of saying, let's guess y equals e to the st, plug it all in. Now we can just read it. You can just look at the ODE and say, oh, its characteristic equation has to be AS squared plus BS plus C equals 0. Okay, so you can read it right from the ODE, write down the characteristic equation, its solutions, which are the eigenvalues, lead you to its roots, which are the eigenvalues, lead you to solutions of the second order ODE. All right, so now that we've developed this shortcut, we're going to use it to study the equation that models the harmonic oscillator a little more in depth. So the undamped harmonic oscillator is where B equals 0. The damping coefficient is 0. So it's just my double prime plus ky equals 0. What is the characteristic equation of this system? Equals 0. So it's important to note, I forgot to point it out at the very beginning. Let me go back to the first slide for a second. M is always positive and K is always positive. Okay. So mass is always a positive amount and the spring constant is measured as a positive value. And B is either 0 or positive. So our coefficients are always positives. So come back here. So my eigenvalues I get by solving the characteristic equation, right? So this says that S squared equals negative K over M. And if K is positive and M is positive, then negative K over M is negative, right? So I get S is plus or minus I square roots of K over M. Because you're taking the square root of a negative number there, pull it out and make it an I. So this square root, the square root of K over M, happens so frequently in the harmonic oscillator example that we give it a special name. We call this omega. So we have S equals plus or minus I omega, where omega just represents the square root of K over M. We do this a lot, mathematicians and physicists and applied mathematicians. When you deal with real life things, you have all these constants. We like to make the math easier on ourselves. We just keep renaming them to make them less ugly, right? So the square root of K over M, we're like, oh, let's just call that omega. So then we have our eigenvalues are plus or minus I omega. So we have solutions of the form y equals e to the I omega t. I know it's crazy, right? But here it is, right? This is the undamped harmonic oscillator. It's got imaginary eigenvalues. Yeah. So we actually have two solutions, e to the I omega t and e to the negative I omega t, right? But whenever your eigenvalues are complex, you really only need to use one of them, right? Because then we're going to separate it out into real and imaginary parts, and each of those parts are their own solution. So when I apply Euler's formula to this imaginary e to the imaginary thing, I get y equals cosine omega t plus I sine omega t. No, Euler's formula just says that e to the I theta is cosine theta plus I sine theta. And then my general solution is a linear combination of the real and the imaginary parts. How what? They are related fundamentally by Euler's formula. Yeah, that e to the I theta is cosine theta plus I sine theta. And we proved it using Taylor series in Calc 2, that they're very closely related. Yeah. It's a surprising fact when you figure it out, but yeah. So my general solution is a linear combination of the real and the imaginary parts of this particular solution. So I'm going to have K1 cosine omega t plus K2 sine omega t. And this kind of makes sense because the undamped harmonic oscillator, there's no friction, there's no energy loss. So if you have a mass on a spring, it's just moving back and forth forever. There's no force slowing it down, trying to stop it. So it's going to oscillate sinusoidally forever. So this is a solution that makes sense, a linear combination of sines and cosines. Omega is what determines the period of the oscillations. And omega was the square root of k over m. So the period is determined strictly by the spring constant and the mass. So these are some pictures of the solutions. We've got the phase plane that are closed orbits, and then the x of t and the y of t, y of t and v of t graphs. So you can see they end up being sinusoidal.
Are those specific omega values?
No, so, well, yeah, for me to make the book to make the graphs, they had to put in an omega value, but they labeled it pi over omega, 2 pi over omega. It's cheating.
Like a omega value.
Yeah. All right, so now let's look at a harmonic oscillator that has damping. This is clearly going to be a more complicated case. So the characteristic equation, read it right off the... Good. So when I solve this, I'm just going to have to use the quadratic formula, right? And I get S equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. Replacing a with m and c with k in the quadratic formula. So here are my eigenvalues. I can't classify what happens, what kind of equilibrium point the origin is, unless I know values for m, b, and k, right? But there's several different cases that can happen, all depending on the sign of this value under the radical. Okay. So if the number under the radical is positive, right? If b squared minus 4mk is positive, then I've got two real solutions. And imagine 4mk is not there. What's the square root of b squared? B, right? So I would have negative b plus or minus b. But b squared minus 4mk is going to be smaller than b squared. So the square root of it is going to be smaller than b. Everybody got me so far? So if you, because all of the constants are positive, yeah. So when I take b squared and subtract some positive amount, I get something less than b squared. And when you square root something less than b squared, you'll get something less than b. Okay. So I have negative b plus some amount that's less than b. So negative b plus that, what's the sign going to be? Negative. Negative b plus a positive amount that's smaller than b. So you end up with a negative. 2m is positive. So in the case where b squared minus 4mk is positive, this is a sink. We're going to have two negative eigenvalues. Yeah. So this, the square root of b squared minus 4mk has to be less than b, which means that we have a sink. Two real eigenvalues, both of them will be negative. Now, if b squared minus 4mk is negative, then this is an imaginary number, right? Then I'm taking the square root of a negative, and I'm going to have two complex solutions. We're assuming b is non-zero, right? Because this is the oscillator that has damping. So the real part of my complex solutions is negative, which means what kind of equilibrium point is the origin? Yep, it's going to be a sink, but it's going to be a spiral sink in this case.
It makes sense.
Right. It's a spring that's damped, so it's going to head towards the origin. Yeah. So it either is a sink, in which case it just goes right to the origin, if my eigenvalues are real, or it's a spiral sink where it oscillates. The spring goes up and down, smaller and smaller oscillations. Okay. Or if b squared minus 4mk is 0, then I have a single repeated eigenvalue, negative b over 2m, in which case I have sort of that almost a spiral sink, but forces it right to the origin. Okay, so we just discussed all of them. If b squared minus 4km is less than 0, then this is a spiral sink. And we call this the overdamped. I wrote it down wrong. But yeah, I think this is underdamped. Okay, so the way that I finally wrapped my brain around what the names of these are is that the point of damping is to prevent oscillation. Okay, you just want, if you were trying to damp the spring, you're just trying to stop its movement. So if you have a spiral sink, then we have all this oscillation, right? So we call this underdamped. There wasn't enough damping to prevent the oscillations, to send the mass just to its resting point. If b squared minus 4km is positive, we call this overdamped. And that's just a regular sink, yeah. And we call that overdamped. We send mass just right back to the origin, no oscillations. And if b squared minus 4mk is 0, this is the repeated eigenvalue scenario, which is like kind of the border between a spiral sink and a regular sink. So this is the bifurcation, yeah. This is sort of between a regular sink and a spiral sink. And we call this critically damped, as in the critical value between underdamped and overdamped. So let's see what these look like. We've got a spiral sink, which would look something like this. A regular sink, which has two straight line solutions. I'm just going to put them in here randomly, that both approach the origin. And then we have solutions that come in parallel to one and tangent to the other. Yes. And then parallel to one tangent. I'm doing it wrong. This is fine. So we're assuming this is the fast. Oh yeah, you're right. I drew tangent to one and not the other. Sorry. Okay, so parallel to this one, okay, so parallel to the fast one, tangent to the slow one. Yeah. Like that. Thanks. And then critically damped, we've got one straight line solution. We'll just pick a random one here that goes right to the origin. And then they all come in parallel to and tangent that straight line solution. So we've got parallel and tangent. And they all kind of swirl in like that. All right, so I typed out a full summary of what all these things say. B is 0, oscillator is undamped, the origin is a center, all solutions are periodic. The mass oscillates forever about the rest position. If B is positive and B squared minus 4km is negative, the oscillator is underdamped. We have a spiral sink. And if B is positive and B squared minus 4km is positive, we have overdamped situation where we just have a real sink, regular sink. So the mass tends to its rest position with no oscillations. And the same with critically damped. It tends to its rest position with no oscillations, but it might go past the origin once or twice, right? So like, it's not going to oscillate. A typical solution in this case would be something like this, right? If it heads towards the origin, it misses, and then it comes down and goes back to the origin. So the spring is going to go past rest, up past rest again, and then settle down towards rest. Something like that. All right, so that finishes up the lecture. I wanted you to do some practice, and I thought, why not just do the homework? So you can look at that, or you can start looking at your study guide for the test.